Well, thank you. I would like first to thank Barbara and Patrick for inviting me to be here. It's a pleasure and an honor. So we'll be switching gears from geodynamics talks to a seismology talk with a little bit of geodynamics. I'll be talking about some of our work on global anisotropy tomography and how it might give us some hints about mantle flow, notably around slabs, and perhaps about how slabs and plumes might interact. A lot of this work was done with a number of collaborators listed here, and particularly Sang-Jun Chang, who was a former postdoc now based in Kangwon University in Korea, and also more recently with Manuele Facenda from Padova University. So to give some very basic background, as you all know, seismic tomography, illustrated here by this now classical global tomographic model, S20 RTS, it gives us a snapshot of the current state of the mantle. So it has really taught us quite a lot about how our planet works, in particular by emphasizing these low velocity regions at the bottom of the mantle, here in red, yellow regions. Also, it has taught us about slabs and how they really definitely penetrate into the lower mantle, so illustrated there with these fast, blue fast regions. So if we start comparing existing global tomographic models produced by different research groups, at least the large-scale features and at least in the upper mantle, when it comes to isotropic shear wave velocity, there's in general a good agreement between the different models. So it is fair to say that at least at the large scale in the upper mantle, shear wave velocity features are now well known and reproducible. Now, as more data volumes have accumulated, it has been possible to go further and to look at other properties, such as anisotropy, attenuation. However, when we start comparing different models by different research groups, there are larger discrepancies between them. Now, needless to say, anisotropy is a very important property to try to map because ultimately it can tell us about deformation, strain in the mantle, and so ultimately it might tell us about mantle flow. Now, the simplest type of anisotropy, as you all know, is the so-called radial anisotropy, so the difference between vertically and horizontally polarized shear waves in our case. And it has been known since the 60s that the Earth's upper mantle is radially anisotropic, so it was, for example, incorporated into PREM. And so in our group, we decided to start by studying this simplest type of anisotropy, radial anisotropy. So, going back to the basics, as you know, the key ingredients to build tomographic maps are seismograms, so here with some body and some surface waves. And so in our group, really, we follow what I would call a big data-driven approach. So we basically have assembled a huge data set of seismic measurements, both of surface and body waves. So here I just give a brief summary of the data that I'm talking about. So we've assembled over 43 million measurements of surface wave phase velocity measurements. I have zoomed here a seismogram specifically filtered for surface waves. And so these measurements tell us mostly about a large part of the mantle. But also we include group velocity data in a wide period range that is not only sensitive to shallow mantle structure, but as well to the crust, which, as I will highlight, is quite important when we are talking about mantle anisotropy. Now, more specifically, when it comes to the phase velocity measurements that we use, we need to use both Rayleigh and Love waves because they are sensitive, one mostly sensitive to SV, whereas the other is mostly sensitive to SH. But importantly, we use not only the fundamental modes arrival of surface waves, which is typically this larger amplitude arrival that you see here, and which is mostly sensitive to the upper mantle, but we also use a massive set of measurements of overtones or higher modes of surface waves, and which in this example here you can see clearly as these early arrivals, and we can show that these data provide a very good coverage and sensitivity to the transition zone and to the uppermost lower mantle. In addition to that amazing set of measurements that we compiled from different groups that have really went through the efforts of making these compilations and these very careful measurements, we also use body wave travel time measurements from a variety of phases, which were measured previously by Ritzema et al. And so this means that we have a really huge, very large data set with a very diverse sensitivity to the Earth's interior, so from the crust to the lowermost mantle. So then when it comes to our modeling approach, this is just in a very quick nutshell. what we do is we invert simultaneously for isotropic and anisotropic structure with this parametrization, but also for crustal thickness. And the reason why we are doing this is because our previous work, as well as from other groups, notably from Barber's group and others, we have clearly seen that when it comes to map anisotropy in the mantle, it is very, very sensitive to, say, errors in the way we model the crust. And so the strategy that we came up with is that, yes, we use some existing a priori knowledge of the crustal structure, but we also allow for perturbations for it in our inversions. And this is a very important point to avoid contamination of unmodeled crustal effects into the anisotropy. Just some technical details here. We start with the PREM model, which, as you know, is, and I mentioned, is itself anisotropic from the Moho down to 220 kilometers depth. When it comes to the spatial parametrization of our model, in terms of depth-dependent properties, we use these 21 spline functions shown here. You can see that the parametrization gets coarser and coarser as we get deeper because resolution decreases. And then for the lateral variations in the model, we use spherical harmonics. It's a natural basis function on the sphere up to degree 35. So we are talking about nominal lateral resolution of in the order of 1,200 kilometers, so large-scale model. But even with this relatively coarse parametrization and solving for these physical parameters, you can see that in total we are inverting for a huge number of parameters. So it's a very large-scale, massive inversion. And so in order to tackle this problem, we use, of course, high-performance computing facilities, and we are very grateful to a number of facilities that we use, a bit like Peter Bunge mentioned in his presentation, but as well, we use some approximate schemes in terms of the forward and inverse modeling. So in terms of the forward modeling, we simulate the data using the so-called great circle approximation. Some of you might not be very familiar with it. It's basically linearized ray theory, so it means that we are using an infinite frequency approximation that only takes into account first-order path effects. And for the inversions, we linearize the problem and we use some least squares optimization. And this really makes the problem tractable, having so many parameters. And it also enables us to do many, many inversions. Each inversion itself is quite lengthy, but it's still possible to do it. And so we actually build, we did more than 100 inversions to build a variety of models, changing the subsets of data that we use and some different changes in the modeling itself. In case you wonder, how wrong are we by using this great circle approximation? Actually, recently, we've done some forward modeling tests with a student of mine, Laura Parisi, whereby we considered existing global Earth models and we perturbed them to become rougher, so with perturbations up to about 20% in VS, which is relatively large, I would say, at a global scale. And so we compared theoretical seismograms computed for this approximation with those computed with purely numerical full wave field calculations. And actually what we showed is that for the type of data that we are using, which are basically travel times or phase measurements from surface waves, and in particular for fundamental mode waves, we actually found that this approximation for these current global models and rougher versions of them actually works quite well. So it gives us some confidence that at least for part of the data that we use, it's still reasonable to use this approximation. So as I said, we've done many inversions, and I'm now going to show you some of our results. So basically, our model is called S-Globe-Rani, and here I show the isotropic structure in the upper mantle. I compare it with the S4-TRTS model, so it's another whole mantle model. And then here I compare with two upper mantle models. So just bear in mind that perhaps the fairest comparison here is really between our model and S4-TRTS because they are both whole mantle model, whereas these two have been specifically designed for the upper mantle. So in principle, they might be better for the upper mantle. And so what we see is, again, these very large-scale features that we are now very well known and well established, such as the low velocities around the ridges in all of them, high velocities beneath the continents. As we get deeper, we start to see quite clearly the signature of slabs here as we reach the bottom of the upper mantle. However, if we look in detail, there are some nice, interesting features there. So, for example, here at 100 kilometers depth, you can see that in our model we have these two low-velocity anomalies beneath Tibet and Mongolia, which also appear in the upper mental models, but they don't really appear in S40 RTS. So it suggests that at least in some regions, perhaps we are getting sharper features in our model compared to previous global whole mental models. As well, we look quite a lot in detail into subducting slabs. Perhaps you can't see it quite well, but in fact, we see really the slabs being very nicely delineated. So these fast anomalies, particularly in the Western Pacific, really seem to follow very nicely the plate boundaries, whereas previous models perhaps are a bit patchier than what we found. Let us now look at the anisotropy. So what I now plot here are perturbations in radial anisotropy expressed by this so-called Xi parameter, so the ratio of the square of VSH and VSV. So just bear in mind that now blue regions correspond to regions of faster SH, which to very first order in the very shallow mantle might be interpreted as some sort of horizontal flow, whereas these red-yellow regions correspond to faster SV, which could be very shallow depth interpreted as vertical flow, but of course this is all very approximate. It really depends on the physics of the minerals. And so what you can see immediately is that, as I mentioned in my introduction, there are more discrepancies between the models. However, there are some common features. So, for example, we see at 150 kilometers depth this faster SH anomaly beneath the Pacific. This has been now, I would say, established for some years. Many regional studies have shown it before. As we go deeper to 250 kilometers depth beneath the East Pacific rise, we also see this faster SV anomaly that seems to appear in every model, which has been interpreted as some vertical flow that perhaps then changes into horizontal flow at shallower depths. And then there are some interesting features that seem to appear in our model. So you see here in the transition zone, we seem to see these faster SV anomalies associated with slabs, and I'm going to show them in more detail a bit further down the line. And then when we reach the bottom of the mantle, we see these faster SV anomalies beneath the Pacific and also beneath Africa, which are also seen in other models. And as I mentioned, we've done many inversions. We've done lots of robustness tests and resolution tests. I'm not going to bore you with all of those details, but there's one specific robustness test that I would like to highlight. So we've done this test, and the Harvard group with their own data sets had done a similar test before and had the same conclusions, which we confirmed here, but I think this is really quite important. So we've done this synthetic test where our input model has the same isotropic structure as in the results from our inversion in S-globe-Rani, so this is at the bottom of the mantle, but we don't put any lateral variations in anisotropy, okay? So we then computed synthetic data as exactly in our real data inversions for this artificial model, and so we would expect to get some sort of damped version of this as output model and no anisotropy, right? And here is what we get from the inversion. So indeed, the output isotropic structure is a damped version of the input one, which is what you expect from your tomography approach. However, in the output anisotropic structure here at the bottom of the mantle, we do find these coherent patterns of faster SV beneath the Pacific and beneath Africa. And by the way, we've done these tests for every single depth in the mantle, and it's the only place where this problem appeared. And so what this is telling us is that basically the isotropic structure in the input model is leaking into the anisotropic structure in the output model. And so if you are wondering why does this happen, why only at this depth and not at other depths, is basically because the body wave data that we use to constrain the lowermost mantle is mostly sensitive to SH type of polarized waves. And so it's a problem intrinsic with the data that we've got available. So that's why it is coming from. So there's an unbalance between SV versus SH sensitive data. And so this is just the same, so input, output. And when we compare the output from this synthetic test to the output that we get from a real data inversion, we see that there's a big similarity. And so this is suggesting that this anisotropic structure that we get in the lowermost mantle is probably a leakage effect from isotropic due to this limited, this unbalance in SH versus SV sensitive data. And so the bottom line here is that we have to be very careful, and it seems that it's quite difficult globally to map anisotropy in the lowermost mantle. So a negative result, but I think an important one to take into account. Okay, so going shallower to the transition zone, so I've highlighted before that we seem to find these faster SV anomalies beneath the Western Pacific, as shown here. As I said, we've done lots of robustness tests, and including these leakage tests, and the features seem to be robust. And if we want to start looking in more detail, we can find some interesting features. So we see in particular that as we go from this 400, 500 kilometer depth range to 600 kilometers depth, the amplitude of the anomaly seems to kind of decrease and then increase again. So what could cause this anisotropy? Of course, this is now interpretation, so perhaps the simplest first-order interpretation could be to think in terms of SPO, perhaps due to laminated structures being transported within the slabs. Most of the slabs really are stagnant in this region, either at 660 or in the 660 as 1,000 kilometers depth region. So that could lead to some, so this horizontal motion could lead to strong deformation. So perhaps that could be one simple answer to it. The other possible interpretation is linked to the mineral physics. So if we think that, so in this depth region here, the dominant mineral phase is Wardsleyite. So there's been this particular study that suggests that for some possible water content, the system of Wardsleyite could be such that this horizontal flow could cause faster SV as we see. Then as we go deeper and ringwoodite becoming the main mineral phase, we know that it's weakly anisotropic, so it kind of matches this reduction in the amplitude of anisotropy that we seem to observe. And the remaining could be just perhaps due to SPO. And then as we go deeper, Bridgmanite is the dominant mineral phase, and at least for uppermost lower mantle conditions, it seems that it is anisotropic. And of course, there are also hydrous phases that also could contribute to our observations. Now, one thing that that when we started analyzing and doing some interpretation on our model, one feature that really jumped into our eyes was a very prominent anomaly beneath the Tonga-Kermadec region. So we've done lots of targeted resolution and robustness tests of this anomaly, and I'm going to show you now some cross-sections specifically for this region. So I show here cross-sections through our isotropic and radially anisotropic structure. So this cross-section here, as you can see, really covers the Kermadec region, which is basically for the south. So it goes from the northeast to the southwest, whereas this cross-section here, sorry, the resolution is not great, grazes through the northern tip here. So it's mostly, really, we are seeing mostly the Tonga region. And so here we've got cross-sections all the way down to the core mantle boundary, whereas the cross-sections through the radially anisotropic structure go down to 1,400 kilometers depth, because below that resolution starts to be not great. So we take the conservative approach of only interpreting down to 1,400 kilometers depth. And the gray dots that you see is seismicity from the EHP catalog. And we've got the 660 here shown with this dashed line. And so there are quite nice, interesting features that appear. So if we look at the isotropic structure first, we see very nicely the signature of the slabs. And we see in particular that the Tonga slab is stagnant at the 660, whereas the Kermadec slab goes below the 660. And these features have been observed before with high-resolution P wave velocity models. Then still on the isotropic images, we see this very prominent, strong, low-velocity anomaly, which seems to come all the way from the core mantle boundary. In the Tonga region here, it seems to really be all the way beneath the slab, whereas in the Kermadec, it's not so much really following the whole slab. We looked at it in quite a lot of detail, and it seems that this low-velocity anomaly seems to match quite nicely with the mega ultra-low velocity zone that has been reported for the Pacific LLSVP. And so we interpret it as perhaps being this massive upwelling that could correspond with the Samoa plume. There are surface observations that seem to match the plume. Now, when we now look at the anisotropy, so remember, blue now is faster SH, red is faster SV. What we seem to see is just like I showed before, in the transition zone, and the slab itself seems to be associated with these faster SV anomalies. And then we have this very prominent, deep and strong faster SH anomaly that seems to be behind the slab, is really quite big. And if we compare the geometry of the anomalies in the anisotropy and the isotropy images, it really seems that the geometry of these anomalies seems to match better the geometry of the upwelling rather than the slab itself. As well, it really goes quite deep below the slab. So our interpretation was that, well, perhaps this is the signature of some strong plume slab interaction between the Tonga slab and the Samoa plume. This had actually been suggested before. So by Mike Gurnis had hypothesized that, and as well reported, for example, that looking at beach balls, focal mechanisms of earthquakes in this region, there seems to be some sort of upward tension there. As well, the Tonga Kermadec setting is quite unique. So, like I said, not only there's the Tonga slab that is stagnant, whereas Kermadec goes below, but also it's a very fast slab. It's the fastest retreating slab on Earth. It has huge amounts of deep seismicity compared to other places. And so we kind of hypothesized that perhaps indeed this is the signature, these anomalies are really the signature of this deep interaction between the plume and the slab. Perhaps the plume plays an active role in terms of contributing to the stagnancy of the Tonga slab. Perhaps does it even contribute to this fast slab retreat and the fast opening of the Lao Basin? So we had this sort of hypothesis from our ideas. So in order to test whether they were geodynamically sort of consistent, we teamed up with Manuele Facenda, who did quite a lot, over 50 simulations to test if geodynamically this could be reasonable. And so here, this is really Manuele's work, not my work. I just summarize his approach for those of you interested. So there are really two key elements. So a dynamical element, whereby he considers a viscoplastic rheology that takes into account both dislocation and diffusion creep mechanisms, where dislocation creep is 5 times stronger than diffusion creep. He includes phase transitions for a pyrolytic mantle composition. And then, on top of the dynamics, he computes the fabric using a basically modified version of G-Rex with some big assumptions behind. And he uses for the slip systems of the major anisotropic minerals, the slip systems that are reported mostly from laboratory experiments. And for Bridgmanites, it's a bit more uncertain. So instead of just choosing one proposed slip system, actually he used the variety of proposed slip systems in the literature from experimental studies and as well ab initio models. And then we just compare systematically the different results from the simulations with the tomography. And then finally, he gets the elastic properties through void averaging. So he gets for me, my interest is to look at VS and the radial anisotropy. Importantly, so he did really lots of simulations trying different parameters, but also importantly, he tested different scenarios like with and without a plume. As well, in this region, another thing to take into account is that there's the Ikorangi plateau that is attached to the Kermadec slab, so he also tested the influence of that, and as I said, the different slip systems of Bridgmanite. And so these are some results from his simulations. So here he considered just these large slabs. So if you want here in the north, it would be Tonga. In the south, it would be Kermadec. Just the slab alone, in this case, penetrating. Then here he considered the effect of the plateau being attached to the south, so being attached, say, to Kermadec. And it was quite nice. You can see quite nicely that the effect of the plateau is leading to this fast slab retreat. Then here, it's the effect of the plume alone hitting the Tonga region, and he found quite nicely that indeed the plume can contribute to slab stagnancy, whereas in the southern bit, say, emulating Kermadec, it goes all the way through. But he did find as well that actually the plume does not contribute to fast slab retreat, but actually to slab fast advance. So this idea that we had, perhaps the plume was really controlling lots of things, doesn't seem to be consistent with the geodynamical simulations. And then finally, in this scenario here, it combines both the effect of the plume and of the plateau being attached to, say, Kermadec. And it seems that with this scenario, he reproduces some of these key first-order dynamic geological features of the region. So the Tonga slab being stagnant and Kermadec going down, and as well this fast slab retreats that is observed. And so when we then compare the resulting elastic properties, the averaged VS and radial anisotropy, this is now here an example for one of the slip systems that he considers. So these are, again, the sections that I showed before. And we can see that at least qualitatively there's quite nice agreement between both the isotropic and the anisotropic structures. So it seems that indeed our results seem to be compatible with the scenario of of interaction, deep mantle interaction between the Tonga slab and the Samoa plume. Also indicating that perhaps indeed plumes, or at least in this setting, are quite dynamic and are not just simple passive features. I think what I quite enjoyed about doing this work is that there are quite a lot of different things that needed to be matched. So the dynamics of the region, the known geological features, and as well not only the isotropic features, but as well the anisotropic features. But of course, there are lots of uncertainties in the modeling and so on, and so it's a possible scenario. In case you are wondering, okay, so that's for Tonga. It's in Tonga Kermadec, a very special setting. What happens for other subducting slabs? So we've looked at it, and this is my last slide. So I show here some examples of isotropic and radially anisotropic sections for a variety of slabs from northern Kuril to Honshu, Western Java here, Kermadec. So I just for reference, I now have plotted the 410 discontinuity 660, and I also plotted the 1,000 kilometers depth because it's a very interesting region. So Carolina, for example, recent work showed that there seems to be a viscosity jump there. And what is quite striking in the images is that we really seem to find, so in the transition zone, upper mantle, we see the slabs mostly associated with these fast SV anomalies, but we really seem to find in the uppermost lower mantle these faster SH anomalies that you can see, pretty much beneath every slab. So I think these are very interesting results. We've been doing lots of resolution tests, and they seem to be robust. And so we are now working on interpretation. And I really believe that the fact that the anomalies tend to be really confined in this region is telling us about interesting processes going on in the lower mantle. So I will leave you with my conclusions, and thank you. Yeah.